And so James Webb was designed specifically to be able to look back to the very earliest times in the universe when the first galaxies were being assembled, if you like, out of the sort of soup and detritus of the Big Bang.
The Hubble Ultra Deep Field, what is that?
So at the time we took it, it was the deepest, which means the most sensitive picture of the universe that anyone had taken. And it wasn't really an original idea on my part. My predecessor as director of the Space Telescope Science Institute, Bob Williams, had really been the originator behind this. And he thought that with a telescope as powerful as Hubble, it would be worthwhile to just look at a blank spot in the universe and expose for a long time and see what was there. And a lot of people criticized him for that, said, wow, it's a waste of telescope time. It's just a fishing expedition. But it turned out to be one of the most important things that Hubble did, because prior to what he did, people thought that there would be nothing. I mean, you couldn't see anything until galaxies had formed. But it turns out that the way that galaxies were created or were formed in the early universes, they started small and they became big. And the Hubble Deep Field, the original one, was able to first see some of these fuzzy structures that no one had thought they could see, and they were there. And then by the time I came along, there were two, I'd say, big innovations that we realized that made it compelling to go even farther. The first is that we were going to put a new camera on Hubble, which would be much more sensitive than the old camera. The advanced camera for surveys is what it was called. And that was put up in a servicing mission in, I think, 2003 or around 2003. So we knew we could do better than what had been done in the Hubble Deep Field. But more importantly, the Deep Field was a pioneering effort that showed exactly kind of what was tantalizingly out there. And we could calculate that if we got much deeper, that is much more sensitive, we might get pretty close to what you would call the edge, where there were no galaxies. So we thought that was worth a shot. And so the Ultra Deep Field was an idea born out of that. I used all of my director's discretionary time for a year. Actually, I cheated a little. I used a little bit more than a year. We exposed for 1 million seconds. And just to fix ideas, I calculated at one point that Hubble Space Telescope time costs us about $10 a second. So that's a lot of money devoted to it. And it was a big success. We could see much farther than what the Deep Field had seen. We saw many, many more galaxies. We saw lots of interesting structures. So it opened up a whole new era for astronomy.
So this Deep Field picture, right? It's beautiful. There's colors in it. When I look up at the sky, I don't see a lot of color. I was doing some basic research because I'm just like a layman, right? And I was understanding that they do something with coloring towards like the gases. They figure out what gases are going to be there, and then they use that to represent the color. But can you explain to me better, like how the pictures get colored? Is that their actual state, or is there post-processing on them?
Well, it's post-processing because the cameras just record, I wouldn't say black and white, but what you do with a camera is you put a filter in front of it, and it just records the light through that filter. But you don't see all the colors at once the way your eye seems to. Now, your eye consists of rods and cones, and they are sensitive to different colors, red, green, and blue. So your eye is seeing the real color in real time. But with a camera like on Hubble, you have it's like a camera on your phone, but it only looks at one color at a time. So we take pictures in different bands, different colored bands with different filters, and then we combine them afterwards. So that is post-processing. And I will say that the Ultra Deep Field tries to get as close to true color as you can get. It cheats a little bit in the sense that we did record light in a band called the Z band, which is beyond what your eye can see. It's in the near infrared. And so we included that band in the colors. So it kind of expands what your eye could see. So in that sense, it's not a true color. But it tries to hue fairly closely to the true color. So red is really longer wavelengths, or red, and blue is really shorter wavelengths, or blue. And it gives your eye when you look at it, a much greater range than what you have. Now, when you look up into the sky, you can see colors if you know what to look for. So for example, I don't know as much about this time of year. In the winter, for example, if you look at Orion, the Orion Nebula, one of the stars up there, Betelgeuse, is a red giant, and it's very red if you look at it. You will see that it's very red. In the summer sky here, you can see Sirius, the dog star. That's a very blue star compared to some of the other stars in the sky. But your eye is not very sensitive to color light when the light is dim. And if you actually go out, like if you were on a camping expedition and you were walking around at night just sort of lit by the moon, your eye doesn't see color at all. It's only the black and white color, the black and white images that you see. So it fools you a little bit. You can't look up into the sky and immediately understand that there are colors coming from the different stars and the objects.
Okay, so then it's not like the gases that they're emitting.
Well, we do take pictures, or the Hubble takes pictures of gases. So there are these large nebulae, which are gases, and some of these gases are heated up because the stars nearby shine on them. And the light from the stars is absorbed by those gases, and then it's re-emitted. It's like a fluorescent phenomena. And in those cases, we do see very colorful images. So there's a very famous image from Hubble called the Pillars of Creation, which is this set of columns of apparently gas and dust. And the picture from Hubble is taken in a variety of filters, and then in post-processing, we make it into a true color picture. And so those gases, that's exactly what you're thinking about. Those gases are emitting colored light because they are predominantly lines or transitions of specific atoms and molecules that have very well-defined frequencies.
It's such a beautiful picture. I got to look at it a few weeks ago when we were doing some of the prep, and then I'm looking at it right now, and it's like unbelievable. It gives me so much inspiration and motivation to want to go out there and explore. Do you think that, do you feel that way? Do you want to go out there? Do you want to get on a rocket ship and go explore this stuff?
When I was a little younger, I had more ambition to do that than I do now. But you can't. The thing is that about the deep field is that the really interesting parts of that are things that you will never explore personally. They're too far away. Okay, I mean, you're really looking at the universe. You're looking out at distances which are measured in billions of light years. And the most extreme distances in there are more than 10 billion light years away. So, that's quite a long distance. Even if you travel at the speed of light, you're not going to live 10 billion years. So you won't explore those things except with telescopes like Hubble and the James Webb telescope, which is designed to go even further than Hubble. And I'll give you a little hint about looking at the deep field to give you a greater appreciation. There are one or two galaxies in there that look very normal, in the sense of if you see these spiral galaxies or you see elliptical galaxies. The galaxies in our local universe are predominantly spiral or elliptical, at least the big luminous ones that you can see. And so this looks very normal to you. But if you start looking a little more closely in the deep field, you'll see there are lots and lots of little galaxies that are completely distorted. And they're galaxies where there are two that are kind of coming together, or they've clearly collided and they've stripped the stars off, and the stars are in long tails, and there are all these little irregular structures. That is something you just don't see today. And the reason you see it in the ultra deep field is because we're looking so far back in time. We're looking at galaxies before they had actually settled down and created, and they had settled into these beautiful structures we see today. And so you're looking at the chaos of the formation of galaxies.
So it's like watching someone's life, but you're like looking from Like if I met you, it would be like you being born. Like I'm watching the
Yeah.
beginning of you, even though I'm in this time and you're in this time at this age. But when I see you, I only see you at the beginning.
Right. So if you were looking at an image of me coming from a star which was, I don't know, 65 light years away, so the light took 65 years to get here, you'd see me when I was 5 years old. And that's the whole idea. Now, of course, you don't get to watch individual objects grow from young to old in the picture. What you're doing is you're getting a sample of objects at different ages. So it's as if you were looking at a population suddenly and you see some young ones and some middle-aged ones and some old ones. But if we look locally at our galaxies, we only get to see the old ones. There aren't any young ones anymore. The universe has gone beyond that. But when you get back deep enough to the ultra deep field, then you begin to see all of the, the babies and the toddlers and the teenagers, and you get to see galaxies at all different stages of development.
Have you ever, obviously people talk a lot about the aerial phenomenon that are happening in the sky, within our atmosphere, because that's been talked about a lot. Do astronomers pick up aerial phenomenon? I mean, they've got cameras pointed at the sky all the time, right? These really powerful telescopes, then they're recording and they're looking. Do they pick up anything that's abnormal like that, or no?
You mean within the atmosphere?
No, well, I was saying lately there's been a lot of discussion that, with the Navy pilots and different people talking about they call it the aerial phenomenon, right?
Yeah.
Where they don't know what it is, but it's messing with their equipment and stuff and they can pick it up. And I'm curious, I hear a lot about it from things within our atmosphere, right? Does it happen with equipment that's looking outside our atmosphere?
Well, not really. I mean, we do see moving objects. So we often see distant asteroids that are transiting the field of view. A telescope like Hubble is in a low orbit. It's fairly close to the Earth. And so you can actually, it's very rare, but you can actually have satellites, local satellites that go through the field of view as you're looking up. So that sort of thing happens occasionally. To my knowledge, we've never seen anything that mimics what you see in the atmosphere itself. And I think the atmosphere is just a rich source of different phenomena that can be mistaken for, UFO means unidentified flying object. So it's unidentified, whether it's flying or not, or it's just a cloud or a vapor or some other phenomena, that's sort of an open question. I am not a believer in extraterrestrial visitation to Earth. I don't think the evidence for it is good. There's a lot of anecdotal evidence of things that people can't explain, but not being able to explain something is not the same as saying that you have an explanation and that's extraterrestrial. That's a bigger leap of faith.
I'm an explorer, so I just take what I am currently experiencing and try to figure it out. But do you think that, this is not like a pro alien podcast. We don't have a huge stance on it or anything like that. We're mostly tech leadership and interesting science stuff. But I am curious, with the vastness that is space, right, and time, do you think that there's other living creatures outside of the planet Earth?
Well, so now we're kind of getting a little bit more into belief and hunches than science, all right? Let me just say that I think it's likely that there is other life out there. I think that the conditions that gave rise to the life on the planet Earth, they're probably similar conditions throughout the galaxy because we know there are a lot of planets. We know there are a lot of planets pretty much like Earth. And it's very, given the huge number of these things, there are, I don't know, 10 billion stars in the galaxy. Given the huge number, you'd think the conditions to create life are pretty common. And then if we look at the history of life on our own planet, life arose pretty quickly. Our earliest evidence for life is so far back, it's just about the only time life could have been created because the Earth was a pretty inhospitable place for the first, roughly billion years of its existence. It was called the Hadean era. It's Hades. It's just horrible. But as it settled down and it cooled a little bit and got a little bit more friendly, life arose pretty quickly. Now, it was very simple life. It was just single-celled life. And that was true for most of the Earth's history until roughly 1 billion, half a billion to a billion years ago. Half a billion years ago was the Cambrian explosion. All of a sudden, single cells got together and became multi-celled creatures, and then we had this explosion of different species. But that was relatively recent. So it seems to me that at least single-cell life should be fairly common in the galaxy.
Have we found any, other than understanding the conditions in which single-celled life can thrive and looking for those conditions outside of Earth, have we ever actually found any single cells outside of Earth, or have they all been in Earth?
All in Earth.
Okay.
Yeah.
Cool.
And we don't even have the technology to detect ourselves around the nearest star. So if Earth were around the nearest star, Proxima Centauri, we don't have the technology to detect, the Lucy show or, television or even powerful radar broadcasts. We just don't have the technology to do that yet. So we can't rule out that there are advanced civilizations nearby. We can't do experiments either that would confirm that.
Interesting. Okay. How much of the sky are we monitoring? Like, I'm assuming we're using telescopes to monitor the sky and to search for things for research purposes, for all sorts of different reasons, right? There's networks of these telescopes out there. How much of the sky on any given night are we monitoring?
Well, the truth is, I don't know the answer to that. I think on the research side, we monitor a modest fraction of it. And I'm just guessing here, maybe 10 or 20%. We don't yet have global networks that monitor the whole sky. That's a project that we're thinking about at Berkeley, by the way. We're thinking about a whole constellation of space telescopes that we could look at the whole sky 24/7, to look for phenomena. And that's kind of very doable now with modern technology, but it hasn't been done. But the reason I don't know the answer to that is because I'm pretty confident that for national security reasons, we have, the military or the CIA has telescopes that monitor quite a bit of the sky, and but that is not published, and it's not. I don't know what fraction they look at.
Yeah, it's probably mostly like near Earth sky.
They're mostly interested in things like missiles and things like that. So they're not looking out toward the heavens so much.
Right. Okay, so the James Webb telescope, is that Hubble 2.0?
Yeah, I think it's fair to say it's Hubble 2.0. So here's, let me just explain for your listeners or remind them that we are in what we call a Big Bang cosmology, which means that the universe is expanding. And it's been expanding since its very earliest creation, as far as we can tell. We have a lot of evidence that that's true, all the way back to a tiny fraction of a second, up to more than 13 billion years, the universe has been expanding. Now, because of that, and because of the way that general relativity posits light that's embedded within the universe, if you have like a photon that's been emitted from a distant galaxy and it's streaming toward you, as the universe expands, it expands in proportion. Its wavelength gets bigger. So if you look at very distant objects, because the universe is expanded by quite a factor between the time the light was emitted and the time it gets to you, that light is expanded too, and that means it gets redder. Longer wavelengths are redder wavelengths, and that it gives rise to what's called the redshift. And the redshift is a very common term in astronomy, and redshifted light just means that the light has undergone an expansion of its wavelength between the time it was emitted and the time it hit you, okay? Now, as you look farther and farther back, of course, the universe is expanded by a bigger and bigger factor. And so ordinary light that we see, maybe half a micron, half of a millionth of a meter in wavelength. If we look back to when the universe was half the current age, it's expanded by a factor of 2, that light is about twice as long in wavelength, right? So it goes from half a micron to a micron. If you want to look back all the way to when galaxies were first created, the universe since then has expanded by a factor of between 15 and 20, according to our best estimates. So that means that ordinary light that we see at half a micron, if it's expanded by a factor of 20, it now has a wavelength of 10 microns. And 10 microns you can't see. That's in what's called the thermal infrared. And so you need special detectors and special telescopes to be able to detect that light. And that's what James Webb is designed to do. It's a telescope which is large, and it's cooled because anything warm will emit light at those wavelengths. And it's going to be extraordinarily sensitive to light which has been shifted by factors of 20 or even more from the time it was emitted. And so James Webb was designed specifically to be able to look back to the very earliest times in the universe when the first galaxies were being assembled, if you like, out of the sort of soup and detritus of the Big Bang.
Have we gotten any images back from it?
We have. I've only seen a couple. I'm not privy to the inside work anymore, but I've seen a couple from my colleagues, and they are just spectacular. It's a very, creating this telescope and then aligning it and making the images good was probably one of the biggest technical challenges that astronomy has ever faced. And the reports are that they've actually done it better than the specifications, that the telescope is delivering much better images than people had expected it to deliver based on their estimates of how hard it was to align.
That's exciting. I got to, a couple years ago, I got to interview Douglas Terrier, who was at the time was the CTO of NASA. And we were talking about how he shared with me about a lot of inventions that happen to get to space, and like for power drills and all of these different things actually end up coming into the commercial world. So we get some interesting technology from the acts of trying to do these difficult things, right?
We do.
Did any interesting technologies have to be developed to make James Webb telescope possible?
That's a good question. And I think the answer is yes. Whether or not this pushes through to the commercial sector, I think is to be determined. We don't know that yet. But one of the things it did is it created a telescope which was made in pieces out of hexagons that were put together, and then it folded up because they had to launch in a rocket that wouldn't take a 6.5 meter telescope. So it folded up. So it had to unfold. It had to completely, assemble itself, if you like, on its way to its final orbit destination at the Lagrangian point 2, or Sun L2. And those are technologies that, to my knowledge, had never been done before. The other thing that's interesting about that telescope is the mirror is made out of beryllium. It's not made out of glass or other metal. It's made out of beryllium. And beryllium is a very lightweight metal. It's extraordinarily toxic. There's only one place, I think, in the United States where there's a factory that actually will work on beryllium because of the toxicity. But it's once you get it done, it's just a beautiful material for a mirror. So that also, I think, it's the first time a beryllium mirror has been put up. Now, Elon Musk has created a new rocket, the Starship. And the Starship is so big that you could put a telescope like James Webb in it without having to fold it up. And so we might see more in the future. We might see even bigger telescopes that are folded up and then put into the Starship to open up.
Did Musk send the first ones up?
No, he did not. No, those were
who got that contract?
Well, let's see. James Webb was launched on an Ariane 5 rocket that the Europeans have pioneered, and so it was launched from South America, from French Guiana.
Oh, okay, that's pretty cool. What is James Webb? Who is James Webb? What does it mean?
Well, James Webb was an administrator. Now, normally, this is I think a kind of a cute story. Normally, astronomers are allowed to suggest the names of their telescopes, and they usually pick famous astronomers, not surprisingly, right? So the Hubble Space Telescope was named after Edwin Hubble. and we have an infrared telescope called Spitzer, which was named after Lyman Spitzer, a very famous astronomer in the last century. Now, when Sean O'Keefe was the administrator at NASA, he decided to break that tradition and to say, we're going to name this telescope, which was called the Next Generation Space Telescope, after a NASA administrator. He was a NASA administrator, which is not too surprising. And James Webb was a NASA administrator. In fact, he was the NASA administrator who made the Apollo program possible. He was in charge of the administration when we went to the moon. And I think it's amusing because, there's nothing particularly wrong with that. James Webb was, by all accounts, an extraordinarily gifted administrator who created the conditions that allowed NASA to really put people on the moon in the 60s. And that's a huge accomplishment. And there's no reason he can't have a telescope named after him. But you can kind of see the human element here, because astronomers will name a telescope after astronomers, and the administrator named a telescope after another administrator.
That's awesome. It sounds like fun. It sounds like a good group of people over there.
Oh, yeah, it's a great group of people. I worked with NASA for many years of my life, and I think it's a great organization. It's really done some extraordinary things for us.
So I've got a couple more questions for you, and then we can wrap up. Is that cool?
That's fine.
All right. We talked a little bit about this James Webb telescope, and that'll be able to see different wavelengths so that you can ultimately see farther back, like towards the beginning of time. Is that correct?
That's correct, yes.
Okay. What information do you hope to learn by being able to do that?
The first thing I think that will be very cool is if we can literally see the edge. That is, if we can look back far enough in time that we see the very first galaxies that are being assembled out of the detritus of the Big Bang. And when we try to look farther, we see nothing, because there aren't any galaxies. James Webb should be able to do that. Then, of course, we have some pretty good ideas of how galaxies are created. There are some quite sophisticated models and computer programs to show how galaxies must have been assembled. There are quite a few details that we don't yet know for sure, because they can only be confirmed by observation, and I expect that James Webb will do one or another thing. It will refine our knowledge so we really understand how these things were assembled. But then there's some kind of tantalizing big questions. In the galaxy formation business, there's some big questions. It turns out that almost all galaxies have gigantic, massive black holes in their centers. It's so common that it would now be considered unusual if you found a galaxy without a black hole in the center. And when I say massive, a small one like the one in our own Milky Way galaxy is about 5 million times the mass of the sun. And a modest to large one is 1 billion times the mass of the sun or more. And so we don't really know how these things came to be. And there is some evidence that the existence of these black holes and the size of the black holes is also correlated in some way with the size of the galaxy and the other properties of the galaxy, but we don't know how that came about. So understanding how these black holes were put together in the very early universe, I think, is a big, big open question in astronomy that we'd all love to see. And James Webb has a shot at illuminating that, at showing us, some of these steps and finding out what's going on. So I would say that's sort of a big thing on the horizon that we might hope for. The Webb telescope, because it's so powerful at looking at these long infrared wavelengths, will also be able to make inroads into understanding things very close to us that are interesting for different reasons. For example, the extrasolar planetary systems. And the planet Earth, for example, we absorb sunlight and we re-radiate it. That's how there's a sort of a balance between the incoming and the outgoing light. All of our re-radiated sunlight is in this thermal infrared region. Most of it is around, between 5 and 20 microns in wavelength, which is much longer than anything we see. The Webb telescope is perfectly designed to study that region. And so there's the hope that if there are a lot of Earth-like planets out there, and some of them are transiting, and there are various configurations that Webb might be able to see, that Webb will be able to make some inroads into understanding these planets. And it's especially interesting if it will not only be able to see them, but be able to take spectra of things in their atmosphere, because it has spectrometers on board, which can, break the light up into very, very fine, large numbers of wavelengths and analyze it finely. And that's how you figure out what elements are present out there.
Do you think we can would these wavelengths that the Earth is the reradiated sun, right? I'll learn how to speak soon, but it kind of gave me this visualization of, sort of like aura coming off the Earth that we can't see, but yeah.
Well, we can't see it with our eyes, but it's easy to detect. Right.
Do we have is that pretty easy to detect with things other than the James Webb telescope, at least for our own planet, or is that brand new technology that?
No, it's been around for a long time. In fact, the first experiments I did when I was a graduate student in the 1970s, and this goes back almost 50 years, were in the thermal infrared. We had the technology at that time to detect thermal infrared radiation. Now, we didn't have cameras. All we could do is shine light through a little hole and detect the amount of light coming through. So if you wanted to, say, an image of something out there at 10 microns, you'd have to move the telescope around so the hole moved around, and you'd record the different light, and then you would use that to create a little contour map. But now we have large format cameras that work at these wavelengths, and that's relatively new technology. And there are strong military applications for this. So a lot of the technology was originally driven by the military need for reconnaissance at these thermal infrared wavelengths. Well, things like night vision goggles, for example, work in the infrared. That's how they actually can penetrate the darkness. They're looking at the thermal radiation. So the technology has been around. It is used on orbit for various things, planetary missions, Earth-looking missions. James Webb, I'm sure, is the most sensitive of this use of this technology to date. But it's not so uncommon, and it's the way that we use to study the Earth's glow, if you like, because the issue of climate change has a lot to do with how much energy is actually trapped before it's re-radiated. And so getting a clear energy budget by looking at the radiation coming off and measuring the radiation coming in is a very important scientific topic.
I want to talk a little bit more about the beginning of the universe, because that's the James Webb telescope. The idea is to look back, right, and maybe see that edge. So I just, as a fan of science, I don't look super deep into stuff, just to be honest and give you sort of context. But I have a general idea of Big Bang theory and the concepts of it. But one thing that I don't understand, I was hoping you could help me, you could shed some light on. So before the Big Bang, I imagine there's nothing, right?
We don't know.
We don't know.
We just don't know.
Okay. So there's not any sort of science about that's currently out there.
There's speculation, and it's more sophisticated than, the word speculation seems to, connotes sort of a complete wild guess. It's not that true, that the case. There are people, the remarkable thing about progress in physics and astronomy over the last several hundred years is our realization that mathematics describes quite a bit of what we see. And once we understand how to apply mathematics to a physical problem, we can then look at pure mathematical results and see if that tells us about physics or astronomy we didn't know. And the answer is yes, very often it does. So in the case of the Big Bang, we have very good mathematics which describes how the universe evolves once it gets started. And we can make predictions about what to measure, all of which have been verified through many experiments. So we have a lot of confidence in this Big Bang picture. We don't know how it got started. We can't look back to before a certain amount of time just right after the Big Bang, and we don't know what came before the Big Bang. But because we have a mathematical framework for describing how the universe expands, and because we have general relativity, which is a physical theory, an idea, a framework for understanding how all matter and light and other forces create within this, people can then extrapolate. They can use this mathematics. And so they create things. There is a concept called the multiverse, which is that our universe is just one of, an infinite number. People can extrapolate back before the Big Bang and say, well, under certain conditions, if I applied this mathematics, we might have something earlier. So there is a lot of speculation, which is based on what I would call fairly sound mathematical reasoning. We do not, however, know if that's really right, because there are lots of ways you can extrapolate mathematics and predict things that turn out not to be true. And it's only by making observations or doing experiments that you can really check it out. We don't have the ability to do that yet with anything prior to this time, just before the Big Bang. But there are ideas about what's going on, and the people who have these ideas, for the most part, are not crackpots.
So we don't really know it before, we know after. Where's the line? How do we know the second of the bang? Do we know a second after the bang?
We don't know anything before what's called the Planck time.
Okay.
And the Planck time is a well-known number. I could probably Google it and just give it to you. It's something like 10 to the minus 26 seconds or 10 to the minus 40 seconds. It's some ridiculously small number. Before the Planck time, we have no real physics or mathematics to tell us what might have gone on. So in the first 10 to the minus, let's say 30 seconds after the Big Bang, it's just a mystery. But once it's beyond the Planck time, we have sufficiently sophisticated ideas about the physics and mathematics that we can then begin to make predictions about what might be happening. And people have been doing this. And we haven't verified everything at the very earliest times. But for example, when the universe was about between 1 minute and 3 minutes old, that's when suddenly it became cool enough that all the early nuclear elements could be created. And it's mostly hydrogen and helium, a little bit of deuterium and a little bit of lithium, not much of anything else. We can predict, based on what we see as the expansion rate of the universe, just what the ratios of those elements should have been. And then we can measure them out there. And they get it right. I mean, it's remarkable how well it works. You can do the same thing going back with the creation of elementary particles like protons and neutrons and electrons, which also had to condense out of this soup. And then as you go forward, when you get out to about 100,000 years after the Big Bang, which is not very long, really, then what happens is you have protons and electrons and neutrons kind of circulating out there, but they're in what's called a plasma. They're not bound. But when the universe cools enough, then the electrons and the protons can get browned into hydrogen atoms. And the helium nuclei can capture enough electrons to become helium atoms that you go from a plasma state, which is fully ionized, to a neutral state. And that gives off radiation called the cosmic background radiation. And we can measure that. And we can show that we know exactly when that happened and why. And that all fits together with this Big Bang picture. So, we've just got, going back to very early times, we have very good predictions and measurements that can confirm them. And what the James Webb will do is will tell us if our ideas about then, once you get all these neutrals expanding, it cools even farther and gravity gets to take over and start collapsing these structures into bigger clumps that wind up being stars and galaxies, if we understand how that process works as well.
What words do we use to describe the matter that existed in the universe at the Planck time?
I guess I would call it an energy soup.
Okay.
You probably didn't have any particles at all. It was just force fields and energy fields. And as the universe cooled, certain fields became more important than others because, the energies got too low for these fields to operate. And that's what happened as the universe cooled. This energy soup condensed into things that we now call matter. Particles, protons, electrons, neutrons, mesons, and then eventually atoms. or nuclei and then atoms. And then eventually these atoms got together and made large structures like galaxies and stars. And as those things burned and created more energy and the universe cooled even more, we got planets. And the remarkable thing about the planets is, at least on this planet, it cooled enough that not only was it atoms and other neutrals, but you started to get molecules. And the molecules give many, many more possibilities for combining and doing interesting things. And that's how life arose. Life somehow arose from the ability of molecules to work together cooperatively to self-reproduce.
Is that energy soup anything that we recreate or experience like currently in our universe or on Earth at all?
You know, that is a terrific question, Joel. And the answer is sort of. So we can create some of these conditions in some of the particle colliders, like the Large Hadron Collider at CERN. And so one of the things that's so interesting about these colliders is we are recreating to some extent the conditions in the early universe. But the colliders we can build on Earth will never be big enough or energetic enough to really probe the earliest times. That would take colliders of the size of the solar system or more, and we're not going to make those. So our knowledge of that era really has to come from people applying mathematics and physics to the early times to make predictions, and then for us to make observations that can verify those predictions in one way or another. And that's one of the reasons we build telescopes, because that's how we figure out what's going on.
Well, that sounds like a great way to end it. You have provided me so many answers to my wildest questions. Did you have anything that you want to get out there into the world before we wrap up here?
I just want to reemphasize that all of this science, it occurs because people are interested and willing to support it. I mean, it's our tax dollars that are supporting it. Now, in the grand scheme of things, it isn't that much. I mean, people make a light of the fact that James Webb costs something like $10 billion. You know, I mean, $10 billion is just fluctuations in some of these budgets that, you know, Congress is putting off for this, that, or the next thing. So it's expensive, but it's not something we can't afford. And I think as a scientist, I'm really very grateful that we live in an era where people are tolerant of this, that they're willing to let us spend large sums of money to satisfy our curiosity. And we hope that by satisfying that curiosity and then telling you what the answer is, that you will consider that worthwhile as well.